Welcome back for what is going to be my least favorite lecture, because I am not a fan of R naught. But we know that everybody knows about R naught now and everybody likes to talk about it. So let's talk about what it actually is. And it's important to start with the definition. So R naught is the expected number. So not the actual number, but the expected number, the average number of secondary cases after introduction of a primary case to a fully susceptible population. That's why the naught, that's why the zero. The idea of R naught is at time zero, you have a fully susceptible population. You put one infected individual in. How many people will be infected by that one person before they recover? That's R naught. The idea is that in a fully homogeneously mixing population, if every one person introduced infects two people more, then you're going to have an exponential spread with a rate of 2, because you've got 2, and then you've got 4, and then you've got 8. And eventually the exponential will die out because people will start running into recovered and other infected people. But the idea is that with homogeneous mixing, you can start with one person and that will give you an idea of how things will work, assuming that homogeneous mixing. Now, when we look at R naught, we can interpret values to give us an idea of what we could expect with an outbreak. Remember, this is expected number, so it's average. So if R naught is greater than 1, you can kind of expect that the infection can invade. If you introduce infection to this fully susceptible population, it will probably cause an outbreak. You'll get exponential spread and you'll see an epicurve. If the R naught is less than 1, it's unlikely that the infection can invade. And by invade, we mean trigger an outbreak and make a big curve. You may see an infection by chance or 2. So you might see this little chain that slowly dies out, but it's not going to maintain and spread in the fully homogeneously mixing population that is fully susceptible. R naught is inherent to what we call the epidemiologic triangle, this host population characteristics, the pathogen characteristics, and the environment characteristics. So R naught is inherent to a particular set of circumstances at a time. What is the population like as far as recovery time, as far as mixing, as far as behaviors? What is the environment like as far as ventilation or cleaning? What is the pathogen like? So how easily does it spread? How long does it stay inside a person? How long does a person stay infectious? All of those things create R naught, but that's at time 0. RE, R effective, is the expected number of secondary cases from a single primary case. And note that we've dropped in a fully susceptible population. R effective is the current expected number of secondary cases from a single primary case. So the idea of R effective is right now, no matter where we are, how many people would we expect one newly infected person to infect before they recover? Again, kind of interpret the same. If RE is greater than 1, the infection will continue to spread. If RE is less than 1, the assumption is that the infection will eventually die out. RE is time dependent. So R naught is inherent to just the epidemiologic triangle. RE changes over time and over the course of the infection as people get infected, as they recover, maybe as they return to susceptibility. So as things change over time, RE changes. RE can also change as we change aspects of the epidemiologic triangle. So if you have a population in which an RE was less than 1 and say you drop mask mandates, all of a sudden RE is different than it was prior to the dropping of the mask mandates, because now the environment is different, and so you can have more pathogen in the environment. So how do we calculate R naught? In an SIR model, and remember, I'm just talking about an SIR model right here. In an SIR model, it involves the transmission coefficient and the recovery rate. Now, the transmission coefficient beta has two pieces, C and P. C is the expected number of contacts that an average individual makes in a certain time period. Let's say your time step is days. How many contacts do you have in a day? So if your C is 3, then the average person has 3 contacts in a day. If it's 10, the average person has 10 contacts in a day. P is the probability that a contact between an infected and susceptible individual is infectious. So assuming that you are infected and the person that you're running into is susceptible, what's the probability that you are going to infect that person when you contact them? So if you run into 3 people a day, and the probability that you are going to infect one of those people is 1/3, you can expect the transmission coefficient to be 1, 3 times 1/3. So the transmission coefficient is basically the number of infectious contacts an infected individual will have in one time period. The recovery rate, gamma, this is also called 1/D, with D as the average duration of infectiousness. So if you're generally infectious for 3 days, then D would be 3, gamma would be 1/3. The R0 can be calculated as C times P times D, or it can be calculated as beta over gamma. Either way works. So if your beta is 1 and your gamma is 1/3, your R0 is 3, which means that for every infectious individual in a fully susceptible population, you would expect to infect 3 more people. And at the early phases in that fully susceptible population, you'd expect each of those 3 people to infect 3 more. So in the next time step, you have 9, and going on and on and on and on. So R0 is basically how many contacts do you have? What's the probability that you're going to infect them with every contact? And how long are you actually going to be infectious? Now note that this does not take into account the changes in your infectiousness over time. It also assumes that the recovery rate is the only way that you're removed from the population. You can change recovery rate using isolation by saying, okay, you might technically be infectious for 3 days, but we're going to find you on day 1 and you're only going to have 1 day to infect people. That will change things. So all of these numbers can be changed, and actually I find it very useful when I'm thinking about designing a control program to look at C, P, and D and think about how I could change those things to improve R0. Now, how do we estimate R0 using actual data? And there's 2 ways in general. The first is this next generation method, which is the analytic solution given your ODE system. This requires linear algebra. Our recommendation as a instructional team, make mathematical friends, physicists, mathematicians. They love to solve ODE systems. Ask them to use the next generation method to find your R0, and they'll be so happy. So make mathematical friends. Don't try to do it yourself unless you really, really love linear algebra. The other way you can do it is numeric approximations. And this is only popular in the exponential spread phase. You cannot do this with endemic disease unless you have cycles of up and down endemic disease. It only works in exponential spread phase. And the idea is that in exponential spread, in the early phases, the slope of the dIdt curve is R0, because the slope is beta over gamma. And if you look at this graph here that you've seen before, I've shown you many times before, this is the SIR model over time. If we look at the very first couple of days of data and we fit a line to that slope, we end up with a line that is approximately a slope of 2. Now this is with a beta of 2 and a gamma of 1, so it works. assuming you have really good data, which we'll talk about later. Now let's talk about herd immunity just briefly, because one of the reasons that we're interested in R0 is that it allows us to calculate herd immunity. R0, RE, herd immunity, these are all thresholds that are guidance for what we would expect to happen. Herd immunity is defined as the minimum immunity necessary for the R effective to be equal to 1. Meaning this is the minimum immunity necessary that you would expect that each infected individual in a population will only infect one more person. Meaning you won't have spread. You won't have exponential spread. It doesn't mean that you won't have spread at all. It means that spread will be even. Each person replaces themselves. If you get immunity above the herd immunity threshold, the idea is that eventually you will see decline in case numbers because you'll be RE less than 1. This assumes it's at the disease-free equilibrium, so it does not apply during active spread. If you have a lot of spread going along, the herd immunity threshold is not really very useful. It also assumes immunity, not vaccination. Vaccine efficacy is never perfect. There is no vaccine in the world that gives perfect sterilizing immunity to everyone that you vaccinate. So herd immunity assumes that you have to be immune, not just vaccinated, which means you have to take vaccine efficacy into account. It also assumes homogeneous mixing and homogeneous immunity, which means that we have to assume that not only are the contacts homogeneous, that everybody has an equal likelihood of contacting everybody else, but also that those who are immune are spread evenly across the population. I'm guessing that you're seeing the problems with this. This is why this is my least favorite topic to cover. But if you want to calculate herd immunity, it is calculated as 1 minus 1 over R0. I'm not going to go into the math of that. It's cool. It works out. At 1 minus 1 over R0, if we get immunity above that level, we can expect that would be difficult for the infection to invade a population. So some ideas of herd immunity thresholds that are out there in the literature, for malaria, we guess that you need 80 to 99% immunity, not vaccination. So you need perfect vaccination of an almost perfect vaccine, or really good vaccination with a perfect vaccine. Given that malaria vaccine efficacy is like 30 to 40%, we're happy with that. We love it, but it's not going to get us to herd immunity. With polio, it's like 80 to 96%, which is why it's been so hard to eradicate. Our vaccine efficacy is much better, but we really do need to vaccinate everybody. Smallpox was much easier. It's 67%. So with an almost perfect sterilizing immunity vaccine, which we had, we could eradicate smallpox because the R0 was lower. And so we could reach that threshold. Measles, we need to get everybody. So any skip of the measles vaccine makes us vulnerable. TB, we have no idea. Really, we just don't know. Fox rabies, if you're interested in non-human diseases, we need 50 to 80%. So think about trying to vaccinate 50 to 80% of a wild species. This is why it's hard to control rabies in the wild population. So the thing to remember in this, R0, R effective, herd immunity, these are thresholds that assume homogeneous mixing. They make a lot of assumptions about your model structure. If you're going to use these, they're just guidelines to, should we be concerned or not? Is this going to be high enough or not? They're not things that should drive your decision making, and they're not forecasting devices. So please remember, these are guiding thresholds only. All right, we'll see you again in a little bit.